So thanks everybody for joining. I'm excited to have the opportunity for you all to ask questions to each other. I wanted to start by framing things a little bit, I guess, by pulling out a detail that was either specifically said or implied in several of the talks. That is this idea that increasingly training these models is obscenely compute intensive, and we're kind of heading towards a world where only a few very, very, very large corporations could possibly afford these things. And given the potential influence of them in society, this is kind of scary news. So I'm excited about the prospect of thinking through and collectively there being a community of people working on technologies to democratize this to some extent, to make sure that sort of everyday people can have some say and some influence and some ability to participate in all this. And Mohanty, I thought it was quite interesting. I had previously been thinking of that primarily from the point of view of the compute requirements, but it's extremely interesting to think that actually the training data, collection of training data, is also obscenely capital intensive. And so being able to identify domains where that can be done in a community fashion is also really exciting. So having said all of that, as I mentioned, the idea here is for you guys to talk amongst yourselves. And I guess I'll ask you, Mohanty, to go first, since it seemed like you had a question for Max at the end of his talk.
Okay, all right. Then we deviate away from my point of interest, but that's fine, because the whole notion of being able to train these models in a distributed way is also my point of interest, except we spent a lot of time on that. Actually, Matt was also spending a lot of time, Matt from Ben and others, a lot on that. But my point was there, if you look at it from a theoretical point of view, it's easy. It's like easy, right? You take all these layers, you put them up across these different nodes, and they all talk to each other. And then theoretically, it just works, right? But then when we started actually working on that, we knew it was difficult, but when we started working on that, we actually were faced with the reality of the difficulty, the engineering challenges that are in there. And you mentioned this whole notion of bandwidth and communication between nodes. And how does that communication happen? Is it a peer-to-peer communication, or does it happen through a relay? These are some of the key aspects which are very critical for us to be able to ensure that these layers in any large deep neural network can actually communicate with each other. Now, there the trouble is, when we are talking about it in our classic academic context where we are showing all our plots, the scales on those plots are always in milliseconds, right? But if you take a large enough neural network, for example, a GPT-3 175 billion one, and then you are computing the overall amount of data that needs to be transmitted for these layers to effectively communicate with each other and then do the forward pass in a sequential, optimized sequential way, then suddenly a millisecond scale does not really work. Except when we are talking about these things and the way we have been imagining it, we are not really used to latencies like these. So there suddenly it completely becomes a different scale of paradigms in which we are operating on. In terms of imagining it, the ability for us to be able to do inference efficiently, especially if we are splitting layers across nodes, or God forbid, training all of them when we are splitting all these layers across all the different nodes, when we do not have millisecond layer latencies in terms of how gradients are propagated between them. And here I've also mentioned this whole thing, right? This is something we put in a lot of effort in terms of simulations and whatnot to actually compute those numbers. And here I am optimistic just because of how those bandwidth or latency is decreasing over time, just because bandwidth is kind of increasing. And another point on top of that, I will just add that point so you can also touch upon that, is I personally have been seeing most of these voluntary computing networks as a large loosely coupled network where all of these nodes are somewhere far away, where communication between them is expensive. But at the same time, the practical reality is, with a little bit of effort, you could have loosely coupled network of really of a large number of tightly coupled networks. Imagine these clusters from universities, clusters from large organizations where they're volunteering 10 or 20% of their ideal capacity. So how does, when we're theoretically modeling all these communication bandwidths, latencies, and so on and so forth, how do we also take into account those network topologies so we can benefit from them that the most?
So I can answer, right? Let me just comment on a few points which you've raised. All of them quite. I agree with the critique for the millisecond range and for the academic level plots which I've shown, but I would like to point out that we've actually measured the latencies not on a millisecond scale, but on a 100 millisecond scale, or even on a second scale. So this is more realistic in terms of internet. And basically, right now the notebook I've shown you on the one on Colab, basically it runs this a similar decentralized training procedure with Moshpit SGD, and as you can see, it updates quite frequently, even if the peers are located in different parts of the world. So we have some participants from Russia, we have some participants from Colab, and it does synchronize and achieve pretty high quality in a given amount of time. Regarding this issue of non-uniform bandwidth, which you raised in the last part of the question. So basically, there is a way to find the optimal network structure, which is adapted to this network topology. For instance, when you are doing all reduce collective operations, which average this vector of gradients, for instance, across all of your participants, you can actually measure the speed, the pairwise connectivity speed between pairs of your participants. For instance, you can just run something like a simple benchmark of internet connectivity. Yeah, and then you're left with the data for your connectivity speed, right? So you know how fast it is to send like a megabyte of data, or like a tensor of activations from this peer to this peer, and from this peer to that peer. With this information, you can actually devise an optimal schedule or an optimal distribution of data across the nodes. This is given in more detail in the Moshpit SGD paper, but what you actually do is solve a very simple optimization problem. This does not involve any deep learning, so you solve a very simple task, like it's linear programming. This could be done in a fraction of a millisecond for any practical size. And from this, from the solution of this optimization problem, you get the optimal configuration. And this is one of the ways, possibly, which allows you to optimize for these tightly coupled clusters.
The second one, for the first one, I'll get back to it. The second one, I completely agree with it. We know for a fact, again, this is an optimization problem. It's actually a resource allocation problem. But my point was there's no paradigms in place, right? Because when we were talking about it in context of, okay, we have this large distributed cluster. I call it a loosely coupled cluster because of all the bandwidth issues. But in some cases, we know, we can measure that. Let's say we have this information available in this large, a large 2D matrix of sorts, right? This is the bandwidth between node 1 and node 2, which is also easy to compute. But after that, we do not have any paradigms on place in terms of building on top of it, or at least maybe I kind of got it wrong in some cases. But when we were exploring, okay, I have this large transformer model where I probably had a more ambitious goal on that front, right? We wanted to put every layer on a separate node. Of course, you can club some of them together, but I understand that goes into the first question that you mentioned. But in a setup like that, the ability to exactly know and that how how best to kind of allocate all these layers, very much like we would do on a large cluster or something, is something, a paradigm like that could hugely benefit many other applications like these.
Yeah.
If I may, real quick, I'm the admin of MLC at Home, which is running currently on BOINC right now with thousands of volunteers. The the issue of distributed training, I don't think we're going to solve in this 15-minute panel. It's a huge area of academic research, and I am very glad to hear that there are people on this panel who are working on solving that problem and potentially using BOINC to leverage the distributed volunteer aspect of it. I know that in MLC, we've specifically sidestepped the problem of trying to train the next large network, and instead are trying to focus on how networks work themselves.
Yeah.
Because when you look at that exponential growth in parameters, it's exponential. At some point, it's going to hit a limit. And a lot of the power of these networks is it coming from the fact that they are so over parameterized, or even Google isn't going to be able to train GPT-4 at this at this rate. So I'd be interested to hear in general, I'm interested to hear what actual BOINC related issues people have had while working on these particular projects. And but I'm also interested to hear what can we do, because we can't just keep adding on parameters over and over and over again. We're going to hit a physical limit at some point.
I want to add one thing though. So at least in the commercial space, not every company has to train models from scratch. So we found that a lot of people just use transfer learning. So that definitely takes out the problem of training from scratch. And a couple of things that also help. There's a lot of research in making neural networks sparse. Right now they are dense, which increases the size of the models, the number of parameters or weights. That's one area. The other things another approach to do is, so if network bandwidth is an issue, we can also reduce the number of times we send the weights back to, let's say if you had a centralized server. And that there is a whole lot of research in delay compensated SGD. That's basically, if we, let's say we send a subtask to a client, the client can train on it many times before sending the weights back to the server. So yeah, so there are other ways of trying to handle the network bandwidth issue.
Curious to ask a quick question about transfer learning. Given a problem and the desire to not have to train from scratch and for some library of existing models, are there methods, particularly algorithmic methods, for identifying an appropriate starting model to transfer from?
Yeah, Mohanty, let me just answer first, because
right,
I have the dumbest. My answer is the dumbest one, because we have this optimal algorithm. It's called for model in Hugging Face models. Try this model out. It's far from optimal, but it will give you the best results. So basically, well, I'm not particularly familiar with finding out the best pre-training checkpoint for any of these tasks. Basically, what is currently being done in companies in the industry is trial and error, because I'm not aware of any methods which are trying to optimize that step, because fine-tuning is usually pretty cheap, and you can try different models in a small amount of time.
Because that sounds like a rough draft version of the hierarchies I was describing to you before, Max, that were implicit in the Marvin Minsky thing, where the trained models are sort of a higher level than the learning. But anyway, that's an aside.
One thing that does help, yes, I agree with Max that it's mostly trial and error, and there are ways people have tried to match the data sets. So if the model was trained on data set X and you have data set Y, you try to do some statistical analysis as to how much X matches Y. And that's one way to then say, okay, I want to use this pre-trained model. But there are also all heuristics.
there is an issue of domain shift when doing fine tuning, but and it has been solved to some extent, but this is an area of active research. If Mohanty has something to add.
Yeah, so as long as it doesn't delve too much into philosophy, but then, okay, all of us agree that transfer learning, right? The whole idea of learning from a model which already knows is something, that is beneficial. And all of us at some point have kind of worked, many of us have at some point worked on that, right? But at the same time, the key question is, how do we kind of create that source model of sorts, right? For example, if you think about constitutions across time, basically someone would come up with the constitution, many other countries would kind of come up with variations of it, so on and so forth. And it suddenly became very easy to kind of adapt a constitution. And that was the philosophical aspect of it. But now going back to it, how do you ensure that the best and the optimally designed constitution, or transfer learning pre-trained model actually exists? And in many of the cases, the push that we have kind of had working for example, these large, billion parameter GPT-3 models, BERT models and whatnot, is around this idea. Can we have this one model? No one uses GPT-3 as such, right? Because everyone is trying to kind of figure out how to adapt it just enough to kind of do a few shot learning, zero shot learning is theoretically incorrect, but few shot learning task and whatnot. But much of the struggle is about having this community resource that anyone can build upon. And and that itself, assuming for a second that all of us are on board that transfer learning is kind of good, something that is going to create benefits for all, but having the centralized resource from which we can transfer the learning is, I think, a key focus, right? And how well we do that as communities is kind of a very important problem that needs contention. It just so happens that a few big corporations right now are kind of building those constitutions internally, and no one has access to them except for an API.
It sounds like from what Ashwini was saying that such a community repository would have to include not only the models, but also the training data to help you to identify
it's more than just that, because how do you know if you're building this base model, how do you know that there wasn't something injected in there? We treat these models as black boxes most of the time. There's this opaque, huge, big matrix of linear algebra, and
there's been some work.
Anything could be in there. They happen to work, but and then we transfer over. So it's a bit harder to do that. Sorry, continue.
Yeah,
okay.
And there's been some works which show that it's possible to actually poison these pre-trained models by injecting some malicious data in them, so that they perform, so that your spam detection algorithms, which are fine-tuned on these models, work. They prioritize some company, for instance. Yeah. As for the constitution.
No, what do you mean by poison the data? It's trained on the data from the web. It's already poisoned. So the question is, we do not know how poisoned it is.
Yeah,
so I was not a broader philosophical question of how biased it is and whatnot. And at least there's a personal stance that, again, in context of when we are talking about how biased is this model and whatnot, it's easy to blame it on the data, but I would rather take the blame on myself. Do we have a good way to evaluate how biased is it? That's a much better way where it can actually work. So yes, again, we will probably be diverging a little bit away from the topic there.
I just want to say that, yes, there's a lot of active research in adversarial, ML, machine learning. I did see a question, I think, what aspect of BOINC would need improvement, or what could help us? One aspect is we are trying to dynamically vary the number of assimilators. And that's one thing. I think there is some issues there that could improvements. Right now, I think in the config file, we have to declare the number of assimilators, which we use as parameter servers. We've been thinking, how could we change that? So how can we, anyway, we can discuss this offline, but the number of servers that you declare in config.xml, how can we vary that dynamically? That's one aspect that would be helpful.
So one thing that I'll mention is I hope you'll all be able to join us next week when we'll have small group discussions that will be a little bit longer for people interested in particular topics, and issues around distributed machine learning, I hope will be one of them. Having said that, I think we're running out of time for this panel. So if any of you have brief last thoughts, please share them, and then otherwise we'll move on to the second portion of the day, which is going to be a little bit of a deep dive into the infrastructure of a few BOINC projects to hear how they're managing the work that they're doing. So any last thoughts?
Sure.
John, you want to?
So, yeah, I just wanted to say that I think it's great that people are looking at using BOINC and the potential power here for this topic. And I also think it's really nice that we're attacking it from multiple angles, both the data set generation side of it, which is really important. That's what we're doing at MLC, as well as how do you do distributed training on these large models? So I'm glad that we're looking at it, there are efforts looking at it from both aspects of that.
Cool. Mohanty, did you have a last comment?
Yeah, my last comment was more around the idea that we never managed to touch upon this idea of synthetic data set generation in the panel itself, which is very dear to me. But I'm actually betting on the fact that if you can imagine it as a framework, it's going to benefit a lot. For example, me as a researcher, I run a very small startup. I don't have the resources of Google, Game, Lyft, and whatnot to be able to collect data sets of that scale, right? I cannot even imagine that. But if you have a framework like that, where anyone who has an idea of any kind of data sets around a bunch of computer vision problems and deep learning, suddenly many more ideas would be explode in this direction, and hopefully all of these data sets will also be publicly available. And traditionally, much of the momentum in the whole field is because of data sets like these, except they were collected with huge amounts of capital investments where people had to go around, collect all these data sets, sit down and annotate. And we actually still do that also for a bunch of problems. So I would hope to kind of figure out a place where we can have a follow-up discussion on that. I would love to kind of gather a lot of people who can catalyze that movement.
Next week, come back next week. Max?
Yeah, I just want to share this. Well, I want to first of all agree with John and said that I'm glad that this entire area of decentralized deep learning is receiving increased attention from the communities, from both the industry and the academy. And I really hope that with the help from other organizations and including BOINC, this entire area will take off, and we'll see large community trained models with the resources that are actually often available but are not utilized.
Great.
So
thanks.
I'm optimistic.
Thank you. Ashwini?
I just want to thank BOINC. It's lots of years of work that we are capitalizing on, and it's amazing. Would love to, to answer your earlier question, would really love to run experiments on actual volunteer computing, like a large network. But anyway, yeah, thank you.
Okay, great. Well, that was really interesting. Thanks, everybody. And again, I hope we can continue the conversation next week in a more in-depth and slightly longer conversations.